Linux is recursive.
Yeah.
That's dangerous.
I mean, you have folders within folders, so the easiest way to handle that is to just open every folder within the same function. I've done that before. I have.
Everyone has.
It's recursion is kind of one of those things where it has real world use, and when you actually do need to use it, it's super, super helpful. But it gets really, really out of hand. We could talk about it forever. I figured this might be the next best logical step. You guys have heard of the Fibonacci sequence by now, I'd hope. Have you ever heard of the Pell sequence?
No. I didn't realize it was called the silver ratio.
It's dumb, is what it is. It's from a series of things called the metallic ratio, or metallic, the metallic functions, I want to say. Fibonacci is this right here, except it's 1 instead of 2. The Pell sequence, which is the silver ratio, is the same thing, except it's multiplied by 2. There's more of them, such as the bronze sequence and blah, 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 and on and on and on. And at some point, they stopped actually naming metals. Anyways, this right here keeps going up. And realistically, the only reason the Pell sequence is important here is because it makes it more mathematically complex. So whereas the actual sequence for Fibonacci is fairly straightforward, fairly simple, this one adds like this much more computational complexity to it, just because you have to actually take the first number that's closest to it and multiply it by 2 before you add. You wouldn't actually think that that adds a lot, but it does make it awfully confusing. So once again, let's pretend like that's not there, and like you can't just, do the math in your head anyways. You start off with 0 and 1. So to get this one, you multiply this one by 2, you add this. So what is the next one? 2. It's not super difficult, no. But then you step down the line. Multiply this one by 2, add that one.
That'd be 5.
5.
5.
Step down the line.
10, 12.
12. You see how it gets just, wait, hold on, there's a 1 before that. You see how it gets just a little bit more confusing the more times you actually, the more depth you actually go into?
Why is it the second number you multiply?
Just because that's actually how it works.
Well, it's so in mathematical terms, when you see in, it's the iteration that you're on. So 12 is the 5th one. And we're doing in minus 1 times 2, so the 1 before times 2, plus in minus 2.
Oh,
so
okay.
in
Just
is
ignore the F. It just means function of n.
Effectively, yes. So this is how this would be displayed if you were, taking an actual computational course and we're dealing with actual mathematics.
Yay.
Yeah, yay, no. We don't do none of that, but I figured I would put it up there because he's right. Mathematically, that's how you should think of it. In right here, in would be what you're actually calculating. So in minus 1 obviously would be right behind it. Whatever your sequence number is, minus 1. The point with Pell, though, is that it's just a little bit more tedious. It's a little bit more computational. Actually, you bring up a good point. Why is it the first one? The first time I tried to just hand derive this, I did exactly that. I started multiplying the wrong number. Computers are better at this. I'm human. What can I say? The reason the Pell sequence sticks out in that case, though, is because it's computationally complex in a way that the Fibonacci sequence is not. Once again, I kind of have the code already kind of laid out for you. But this is going to be a little bit more complex to step through. Do you agree? Yeah, just a little bit. It's not super hard. You would make that little change to a piece of code. Let's see. Yeah, okay.
So this means it exponentiates twice as fast, basically?
This would...
No, it'd be more
Nope, not twice. No, it would be a little bit more than that, I think. Actually, you know what? Let's not bother. So,
Call it on 30 and
well, why not just change the code?
It's
That
a bit,
way-
it's
that
a bit
way
more
we-
than squared.
Hmm?
It's a bit more than squared.
Just a little bit more than squared. That sounds about right.
Because you check, because the fourth number in fib is 5. The fifth number in fib is 5. The fifth number in pel is 29.
Yeah.
Ooh.
25. That's a
It
little bit
gets
more than
fast.
squared.
It
What's
gets
the
fast
sixth
quick.
Number though. If 29 is the fifth number, what's the sixth number in hell?
The sixth number is
29 times 2.
70.
70.
Okay, so
I wrote
yeah,
fast
okay.
So you know what? Before we actually do that, let's bust back into this just because I'm a Fibonacci and why not?
12.
Now let's talk about X Fibonacci. X Fibonacci is awesome because this goes on forever, and these sequence numbers actually matter. I'm sure if you're doing the right thing. Here's the Fibonacci sequence. There's the code for it. That's everything. This will get you the first 10 in the Fibonacci sequence. Big whoop. Not really that impressive. Hell, it'll do the exact same thing. Here's the code for it. It'll get you the first 10 in the actual sequence. Here's where we get a little bit more interesting over here, because say that you wanted, instead of this, you didn't want the metallic ratio for like 2, you wanted the metallic ratio for like 37. Does anyone want to play that game? Because I certainly don't. All of these different sequences are something that have to be derived, but to derive them, you first have to actually step up to them. Just like the Fibonacci sequence. We know how the Fibonacci sequence was made, yes? Yes, kind of, a little bit?
Yeah, by Fibonacci.
Exactly. It's that same sequence that we've seen 500,000 times. You start out with 0 and 1, and then what do?
Add them together.
You add them together. Easy enough? Okay.
Hey, what's that y after the comma in x bond parentheses x minus 1 comma y? What's that y?
so he's passing y to the function every time.
That was something that was supposed to be expansion that accidentally made it into my code, I believe. I don't believe I need that. For the same reason I don't need to say put hell there. But, whatever.
Well, okay, but
All it's going to
you
do
do
is
need
print out
y.
what y
It's good
is, right?
to pass it.
Yes.
So instead of timesing the last number by 2, he's timesing it by y, whatever you chose y to be, whether it be 37, 2, or 1, like the original Fibonacci. Because any number times 1 is just that number.
Right.
So it's just what? Yeah, it's just
So
whichever step you want to take.
You could
Exactly.
run xbond with a y of 1, and it would return exactly the same thing that Fibonacci would return.
Realistically, yes. Anyways, back to what we were actually, the complete sidetrack. You follow the same mathematical formula for all of these. But for all of these, you are required to follow that same mathematical formula for all of the previous numbers as well. So like I said, Fibonacci, you start off with 0 and 1, and then what do? You add them together. You get 1, you add them together, 2, blah, 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 on and on and on. For Pell, it's a little bit more complex, but I mean, once again, you do the same thing. 0, 1.
2.
Yeah,
1
2,
times 2 plus
5, on and on and on. Start out with 0 and 1 for 37 Fibonacci.
5. 37.
37 is going to be the first one.
And I'm not going
And what's
to
37?
And nobody wants to play that? Come on.
37 times 37? Ridiculous.
Well,
Something
That's
over
what it's
49.
called.
yeah. Who cares after this point?
Yeah.
Sometimes
Sometimes complexity is good.
complexity
Or
is
what
good.
you need.
In this case, coding complexity, though, is going to suck. Because you have to go in and you'd have to redefine what it is every time.
But complex for a computer and complex for a human are different.
Very, very different. We keep trading off. I think this is funny. So actually, once again, let's just go ahead and modify this piece of code right here to get us the Pell sequence. Yeah, it's still going to say fib. Yeah, I have Pell, but it's not exactly hard. I literally have to add like 2
2
things.
characters.
Times
Yeah.
2.
Yeah.
Asterisk.
Do it.
So down here, we're looking for the Fibonacci number of 30. Does anyone wager a guess what it is?
You already ran it.
I already
It's like
ran it. It's
80,000.
that number.
830,000.
Oh, yeah. Just take that, sucker. So with this sequence in mind, you take this little thing that you have to do. What is the difference between the Fibonacci sequence and the Pell sequence?
Asterisk 2.
Yeah, that's literally it. You take the position right behind it, you multiply it by 2. Suddenly you run this code, and that's a lot bigger of a number, but now you have it modified in a way that tells you
It's 12.
a completely different answer based on exactly what you want it to be. In this case, this one is the Pell sequence.
It's literally double the amount of digits.
By the way, if anyone was wondering, Python handles large numbers very well. I don't think there's actually an upper limit on what number you can use, unlike other programming languages where there's a max number you can use. However, if you do start using a million zeros for a number, massive number, Python will handle it if you have the memory for it. It'll probably saturate, 60 gigs of memory, which you probably don't have.
Okay.
But Python will handle it
But it'll
eventually.
do it. So just to once again, let's mess with this and let's bump it down to 10
I'll
just
go up to
because.
50 and see what memory does.
No,
He said.
no, just no. So okay, so the Pell sequence, the 10th number in the Pell sequence isn't going to be that impressive. It's like 2,000. Anyone? I would wager a guess to say that the answer is probably not out there on the internet. So 37 Fibonacci. I dare somebody to tell me this before I can actually do it. Give me a second.
You
Okay.
can't even.
I'll
It would
wait.
take forever to
I'm
compute.
sure it's on the internet. They have like pages where it's like 1,000.
Oh, hey.
They
A
have-
lot shorter than expected.
It's 10. It's the 10th position. That's why I changed it to 10.
You want to
3
do
more
this big
digits.
number?
130 trillion.
Let's do a bigger number.
Whatever you want to do.
Do 20.
Let's wait till we introduce the time metric. For now, it's worth mentioning that the metallic ratios, it's a very simple code tweak, but you understand that to tweak that code, it first has to literally derive everything under that code.
I think you've got like 30 minutes.
Huh?
I think you've got like 30 minutes.
I don't
What is
know.
costing?
27 minutes.
27 minutes. Yeah, that works. Honestly, we're probably right on target then. So.
Fun.
So this is going to be the fun part because this is the part where I get to tell you how incredibly inefficient my code specifically is. Like I said, there's better ways to do that and more reasonable ways to do that because, I mean, sure, mine doesn't take very long to code, but it takes forever to actually get an answer. So if we take this section right here,
Oh, yeah.
is that,
Comment.
wait, hold on.
You're running that on Xbon.
Yeah,
That's fine.
that's fine.
I'm running on Xbon.
I'm still printing everything. Well, see, I don't want to run it like that one though.
You don't want to print it?
No, I don't want to do Xbon. I want to
Just
this
change it to
one,
fit then.
ItterFit. That's what.
Oh,
that's the one I want.
okay.
Get it right, Cheers.
Okay. Hey.
Uncommon. True.
Okay, so this time we're going to do something slightly different. This one, there we go. That one right there, so I can keep track of it, is the iterative version of what we just did. If you'll recall earlier, I said the recursive way of doing it is not always the most effective. In this case, it's not. So the initial part of ItterFib, it's the Fibonacci sequence done iteratively. In this case, we start off with 0 and 1. And as the code says, you take X and you append ItterFib position where I am, -1, -2. You add those together and you append it to the list. Super difficult? Yeah, no, not even a little bit. So you guys remember how long it took to do 50?
To 300.
Honestly, with this one, you probably could. Because this one doesn't really take very long at all. Because the
Except for
numbers,
printing. Printing takes
while.
Okay, well, fair. Printing does take a while, but this can get to the end
Wow,
of that.
you see how big those numbers are?
Yeah, they're.
Just print it at the end.
I mean, I could, but why would I?
Because look at this.
It is
So
chugging.
printing,
It is chugging. It is going very badly.
printing in Python is fairly slow.
I'm going to point out
I
that
have
it's
that
it's
down.
already done with 300.
Oh.
So
Hey.
iteratively, this is far, far faster because it doesn't have to derive everything.
It just remembers what the last two were. Instead of having to get the last two, it remembers what they were. It probably takes up a lot of memory,
Oh,
but
of course, I probably nothing in terms of
well, it's already crashed.
yeah.
It's
Okay.
already-
Well, it's too late. I tried.
Sorry to give it
He's
a
I tried. Whatever. The thing here to remember is iteratively is going to be a lot different. And in this case, it's not really a super good example, simply because, yeah, you could come in here and you can modify your code here just as easily, times 37, literally right there, and then we'd be fine.
Yeah.
But that's just a way of saying that almost everything that you can do recursively, you can do iteratively, so long as you have almost. And a lot of times it's better. It's just more code sometimes.
And sometimes for loops aren't the way to go. Like earlier, he said deleting folders. So if you have a folder and it contains a bunch of folders, and each folder can contain a certain number of folders, you could say four folders in a certain folder, and then have another for loop in that for loop that deals with all the folders in those folders, and then have another for loop in that for loop. But eventually you're going to have a bunch of for loops, and it's going to get ridiculous. But if you instead have a function that does whatever you want, and then just call the function for each folder, you end up having a function that calls itself, which is fine. That's what iterative is about. And that is one situation. Sorry.
Words.
Recursive
That's what
is
recursive
about.
is about.
And that is one instance where for loops aren't quite going to cut it.
So
Good?
would,
Yeah.
Okay.
would recursive only go into if and while loops, not for loops?
You could do for loop.
You could. It would be the difference of having. The real key to recursion is when you don't know what all the layers are. It's really hard to come across things like that. Folder structures are actually one of them that is incredibly pertinent, because say you had a folder called A. Guess I should fix that.
This is going to be good.
This is going to be bad. There we go.
Go ahead.
Say you have a folder called A, B, and C, and under each one of those folders, you had some letter that you have absolutely no idea what it is, but it's some letter, the number 1, and also a folder called Cute Kitty Cat, because everyone loves cute kitty cats. And I'm bored, so cute kitty cats is what you get. Everything else, all of these folders have things in them. You don't know what they are, but they all have something in them. And inside of each one of these folders, you have more things, and more things, and more things.
Each one of these could have more things in them.
Unto infinitum.
You're looking for one file and all of them.
No, not even necessarily
Or
looking
all
for
of them.
Or
Yeah.
all of them.
Or all of them. You just want a list of all of the pictures, which makes this even more ridiculous. Say that you wanted all of the pictures of cute cats that are inside of A, B, and C, literally anywhere. To do that in code, you would have to write, okay, so for each in the sequence of A, B, C, and then inside of that, you would have to do for each inside
each.
in
It would be
each.
like an index of A, B, C, wouldn't it?
inside
Yeah.
of,
But
Inside the index of A, inside the index of B, inside the index of C, and it would go on ad infinitum.
yeah, it would. And you would have to write each one of these for loops. I mean, who wants to do that? Whereas with recursion, you can just say, okay, well, I have this base structure. I will just feed it this base structure, and I will say, okay, A, B, C, and for each in ABC, I guess it would just be another for each in.
you do the parent folder. You pass the parent folder to the function.
Well, in this case, A, B, and C are the parent folders, so all the
What
same,
about
you
A,
would
B, and
just,
C's parent folder?
Root
Root
my
folder.
computer,
Yeah,
or whatever. Big folder.
You don't want to do recursion on root, actually. That's
Tree.
pretty dangerous.
No, it's not.
Actually, we have a great example for that. Just run tree.
Fair. Ew, yuck, tree. Has anyone ever tried to look like a hacker online?
Yeah, you
Try to?
change your font color to green and then do it.
Sorry.
And just smash the keys and be like, I'm in.
So on.
Oh, wait, no, it has to be, okay, yeah, so I
So
didn't change my font color, but yeah, effectively.
I'm hacking you.
I'm hacking you, bro.
in Windows, there's a
Yeah,
function
delete your system 32.
or a command line program called tree, and it just does for each folder and for each folder within that folder.
And for each folder,
Yeah,
and
my
those
font
folders,
files.
ad infinitum, as you said, it just lists stuff. That's effectively what tree does.
You will run into this problem if you program very far. Eventually, you will hit a problem where you don't know how many layers deep you have to go.
It's good for search, like with heap and stack and stuff like that, but that's way beyond this.
Sure,
Yeah.
ideally. But eventually, you never know when you're going to run into these problems.
A nice tool to have in your toolkit.
Indeed. So I think we've covered this ad infinitum, and nobody wants to hear any more about it.
Probably.
So instead, this
Want
is
to
the
do
fun.
Well, Factorial.
Factorial is honestly just another one. Factorial is actually one that you end up doing in crypto. Anyone know what factorial is?
Statistics
Oh.
This is true. So statistically, there's a lot of times that you have to
I know what this is.
you have to calculate odds.
Yeah.
And to calculate odds, sometimes you have to take one away from that set of odds. So effectively, if you, I think rolling the dice is this way.
Bit size
Yeah.
is factorial. 64, 128, 256,
It is indeed.
512.
For any specific thing, like if you're rolling a six-sided die, the chance that you would actually get anything but the number 6 on a six-sided die would be 5 factorial. Because it would be every side of the die, the statistics of getting every side on that die, multiplied by the statistics of getting every other side on that die, except for 6 in this case, because that's what you're actually looking for.
For statistics, the mathematical formula is different on whether you want to allow duplicates or not allow duplicates, and
It gets a lot deeper than that,
Yeah.
but the basics of it is factorial.
we're not in stats.
Thank God. We're not qualified. Go talk to Tiffany.
The easiest one is 4 factorial, which just means 4 times 3 times 2 times 1. And then the problem is that you don't know how big of a number they're going to specify. They can specify 131, and you need to recursively call the function that calls the function, aka itself, to get all the way back down to 1 and multiply by each time.
Right. So in this case, you have a ever-changing set depending on what exactly you're trying to get. It's not, a hard set to come up with, but all the same.
So say you have like a 6-digit pin,
Mhm.
what would the factorial be for like each of those numbers?
So
If
6,
only we had a piece of code to find that out. Let's see. That was the wrong one. Did I write factorial? I do. How about that?
pretty sure Python has this function.
It does. It does. First, let's get rid of that because we don't want that running.
Not to be confused with factors, which you also probably use recursion for.
Would you? Yeah. Let's see.
Well, I get.
Meh. So I probably should have print statements in mind for each one of these, but
No, don't worry about it.
that's laziness.
Oh, there you go. Yeah. What do you want to do it on? 5 or 6?
You said a 6-digit PIN, so
720.
Or 720 different possible combinations.
yeah. That doesn't
No,
sound
no,
right.
there's a
Yeah.
million possible combinations. What he's saying is the recursion of the letters 6 goes to 720.
Well, yeah, 6
six
is what I'm
factorial.
effectively saying is 6 factorial. Is
Yeah.
That's all I'm really saying.
I believe
That's an
that this-
important point to take away from it. It's not the possibilities of the number you put in, it's the factorial of it.
Right. I
In this
believe
case.
720 is the number of combinations if you don't allow duplicates and the order doesn't matter. AKA 1, 2, 3 is the same as 1, 3, 2.
Right. Factorial is a little bit different statistically. Like I said, there's a bunch of stuff that goes into this, but factorial is what we're dealing with at base. And for this one's going to run quite a bit more efficiently because it doesn't have to rewrite over itself 500,000 times, but it's also worth mentioning that all it has to do is derive what's right below itself so it can derive what's right below itself. And then it has to do that and multiply it God knows how many times in this case. Factorial is just another good example of it. So before I bore you all to sleep, blah, blah, trees.
This is the last one.
Is it? I don't actually know. Let's look at my ultra boring slides. Yeah, it is.
All right.
It is.
Cool. Trees.
Trees.
Wow.
Wow. Man.
You guys know what a tree is?
No.
Is it green day outside?
That's actually it. We're done. Yeah. No, open.
You're right.
I think I might give Kim spiral. Yeah, okay.
Just wrote it.
Turtle.
So for this part,
Makes a tree.
ideally, yes. You'll notice I said ideally.
Dun, dun, dun.
What setting do you have it to? Make it something reasonable and then run it.
And then run it. So, well, do I want to explain it first, or do I want to just run it? So
Run it so they have visualization and then explain it.
Okay,
I agree.
because it'll probably take a minute. Let's
True.
see, 10. Yeah, that'll be fine. Here's to hoping.
All right. Make it big.
Big enough. That's good. So this is Turtle. Like we said, this is Turtle recursively drawing a tree. Per each branch, there's more branches, just like on a tree. The basic shape of a tree is made out of several smaller shapes. We call those sticks. The basic shape of a stick is made out of several smaller sticks. They're called branches. On and on ad infinitum, as he said. In this case, it is a simple structure repeated over and over and over and over to make a larger, more complex structure. Something that recursion is excellent at doing. Is this the part where you talk about video games because recursion? Minecraft,
Yeah.
recursively generated?
Is it? I don't know.
I'm pretty sure. The train in Minecraft, recursively generated. It's the same basic function over and over and over again to give you unique landscapes. What's another one? There's several of them.
I wasn't expecting video game talk.
Well,
But
I mean,
you see the base shape? How there's a line and then 4 lines? Well, each one of these 4 lines is a basic shape of a line with 4 lines. And then each one of those is a line with 4 lines, aka recursion. The function, which I'll show you, is just calling itself each time it wants to draw a branch, and each one of those branches has a branch of branches.
precisely. So let's see. Up here, we're defining something called segment because I figured, I didn't want to get too fancy and call it branch or anything. So for this specific part, it's calling itself to create segments of itself, because like I said, a tree is just made up of several different segments, whatever you want to call those segments. I cheated a little bit, and I actually made the trunk completely independent, so we'll ignore that for just a little bit, but we'll come down here, and we'll notice that it calls itself several times per this piece of code, but every time per this piece of code, it drops the size. Size in this case is what controls what is effectively the end of the function.
Once size drops below 0, then we're done.
Something else you have to understand about recursion is incredibly powerful and how it can run, but you always have to give it an end metric. If you don't give it an end metric, it will run forever, and that's not recursive. Well, I guess technically it could be, but you'll never get to the end. It won't be any good.
It'd be like saying while 1 equals 1.
And while that will print 1 forever, that doesn't do anyone any good. So in this case, once again, you could call it cheating. You can call it sketching it a little bit, but all the same, you can look at this and you can see as soon as I actually start off this actual definition, this function, the first thing that I do is say, if size equals 0, stop. And you'll notice that's the whole code block.
Yeah,
If size equals 0, I literally want segment to do absolutely nothing. You'll also notice that since size is equal to 0, or in this case less than 0, because technically it could be, but we'll get into that later, that is automatically going to be the thing that is going to stop your code. Like I said, every recursive block needs some metric to stop by. In this case, every time I call it, you have to take a little bit of that size off, otherwise it'll never stop. The first time it's going to run, let's see, what do I have it set to? 1090. Yeah, okay. So it starts off at 10.
Oh.
The first time it runs, it's going to drop in there with 10. It's going to be fine. And every time it runs recursively after that, it's going to be -2. Not super difficult by any means, but all the same. Let's see.
Some recursive functions will use a variable called depth instead of size and just decrease it by 1 each time. So long as it changes.
Yeah, depth is definitely the standard, because recursion depth is what you actually want to watch out for. Let's see, recursive trees. I guess I could just, I could just drop it to where it's like 5. That's going to be.
When does it set the size variable? When you call
segment, you give it the first variable you give it will be size.
Right. Right up here, if you look at the definition, it gives size and spread. There are 2 variables that control 2 different things, but ideally we'll kind of touch on both of them, because one of them is effectively acting like the recursion depth, so effectively how many branches we want it to have, and the other one is just acting as a control metric for exactly what you want it to look like. So the cool part about recursion is being able to change it in one place, and it just makes a world of difference. So say that was sitting at 10, so we changed it to 5. Your picture is drastically changed.
A lot smaller.
It's a whole lot smaller. So anyone wager to guess what it would look like if it was 2?
It would just be the first couple. It would be the first line, basically, because it minuses 2.
That's it. It would be 1 branch just sitting there, just bored.
my dream.
Super boring.
It dreams of being a giant tree.
Someday it dreams of being a giant tree, and as it grows, soon it will get to 4, which is just a little bit bigger. So the cool part about it, like I said, about recursion, is you start getting some crazy wonky stuff that you don't necessarily expect. You have an idea of what it's going to be, but you don't necessarily know what it's going to actually give you. Specifically, let's see, we started off at 10. We don't want to be here all day, so let's give it, there's one minor, oh God. There's one minor problem with Turtle, and it's that it's incredibly slow. Who's ever seen a tree that looks like that? It's yeah, I suppose.
I mean, it's not done yet.
It's not. Oh yeah, it's gonna take a while. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9 segments in it. It's gonna take a minute. It's not even done with the first one yet.
It's just a tree you're in a hurry.
It's just give it time. All of that to say, we changed one thing, and now obviously it takes so much longer to run, but it's going to be so much more complex of a picture as well, because if we nope, it won't let me make it any bigger. So that's it. That's all you get. That's what I get for not putting
can't wait to see
scroll
that
bars in
tree.
here. Yeah, it's gonna be a minute. We're probably gonna kill it before that happens.
Yeah.
We'll stick around for the different trees later. So let's stick to something slightly more reasonable, like I don't know. Anyways, that's kind of the depth model. The depth, you're going to get varying results based on exactly how complex of a picture you want, and in that case, that's controlled by a variable called size. It's not hard to change. You just saw me change it, and the end result was
Sideways tree.
a sideways tree, right? And we didn't even let it finish drawing. It would have taken forever. The other part of it is this, and this is a variable we call spread, and you'll understand why here in a little bit. So I want to say it was what, 90?
Yeah.
So let's do something like 30.
Not so spread out.
Not so spread out. So like I said, recursion lets you change these metrics to make it to where you can draw something in like 17 different ways. That is no longer a tree. That looks more like the, I don't know, a top head of wheat, maybe. So it's variable unto unrealistic proportions. You can draw so many different things based on something like that. Let's see. This is the part where I get to admit my own failings. So 180 is the bad one.
I think
So let's do
300.
300 might be boring because it's going to be so close to the.
But not fully.
Yeah, okay.
So just a
Anyone wager a guess what 300 is going to do? Not looking at the code?
This tree is going to look nothing like a tree.
It's yeah, you're probably right.
more like a bush.
It looks like an amoeba.
So
It's my DNA.
with these weird patterns, you can still see the basic shape. It's not hard to see the basic shape.
It's already done.
Oh yeah, it's only set on 8. Let's take it up.
Actually, that looks like a beetle.
Yeah.
It
It makes a
little
cool
bit.
pattern, but that's not a tree. That's not a thing of nature at all.
And you don't know what you're going to get out of it. That's, like I said, that's the cool part about recursion is I made this, and even I had absolutely no idea what was going to come out of it.
If you're really good at chess, you might be able to predict it.
If you're good
Yeah,
at
yeah.
chess.
Because even
chess
people
here.
that are good at chess have to have
Yeah.
a little bit of leeway, and this can predict to an
Yeah.
This is
undo.
exponential.
They have a better chance than I do.
Every turn has 4 more turns.
Oh, it's going to be an even darker beetle in the center. It's going to keep going back to its original
Circles is ridiculous.
iterative point.
Yep. Here's where we get to bring out.
You want to break out better circles? Or
Do we want to do better circles? Let's do better
We
circles
did
just
better
because.
circles in here one day.
Oh, did you?
Yeah,
Okay.
Dewey did it for us, but it was cool. I mean, unless everybody.
Is it yours? You ran yours? Oh,
I brought mine, but yours is right there. I don't know.
I wouldn't
I don't know
really
if you
want
drew.
mine.
I don't
Really
know.
just yours with a small edit.
Well, whatever.
Yeah.
Actually, yours probably illustrates it better. All in all,
So each circle draws 3 circles.
it's not exactly a complex thing to do, but once again, if done recursively, this takes significantly less code. And also you end up with this funny triforce. So, I mean, there's that. Is it getting close? What time are we supposed to be out?
Now.
Now?
45.
Okay, well, if you guys don't want to listen to me talk anymore, you are welcome to leave. That's recursion in a nutshell. I hope you guys enjoyed. So, c'est la vie. Yeah,
Believe in the Triforce.
Well, that's because mine was 4
Yeah, yeah, that's because yours is boring. You mispronounce boring.
Darn threads, am I right? Hidden processes and threads.
So let's see. How do I stop this?
You don't.
Just let it record forever.
Oh.
Oh, you go back up to the top.
More. No, pause.